Let's try to solve this problem here. A cylinder fitted with a smooth piston contains 1.2 mole of ideal gas. So right now you have a gas container with a piston as the cover. Then inside there's 1.2 mole of ideal gas inside. Initially, the gas had volumes of this volume and a pressure of 38 kilopascal. Okay, the gas expands isothermally until its volume becomes this volume and then heated isovolumetrically back to its initial pressure. Well, there's a lot of information inside just 2 to 3 sentences, so let's unpack it in the form that is more readable. So what are we going to do? We are going to make something like a table. So we know that initially the gas we know that it's 1.2 mole, so let's write it down. 1.2 mole. Then it has a volume of 7.2 times 10 to the power negative 2 meter cube. That's the correct unit, so we don't need to convert it. So the pressure, they tell us pressure, you usually put it first. Pressure is 38 kilopascal, so let's write it as 38 kilopascal. Okay, so usually what I will do is I will write down the pressure, volume, and also the temperature of each state that you've passed through. So this is the initial state of the gas system. Initially it was in this state, so I label it as A. Then after that, we know that the gas expands isothermally, so we are going to say isothermal expansion happens here. Isothermal expansion. And then you enter state B. Okay, so let's label clearly this is pressure of A, volume A, and temperature of A. And now you're going to enter a new state, so we call it as pressure B, volume B, and also temperature B. So we know that the gas expands isothermally. So isothermally means by the new temperature here should be the same as the old temperature, because the temperature is kept the same is in this process over here. So you can say that TB is equals to TA. Okay. Let's continue. Its volume becomes 22.5 times 10 to the power negative 2 meter cube. So that's volume of state B. So 22.5 times 10 to the power of negative 2 meter cube. Okay. And then they didn't mention the pressure, so we leave the pressure as empty. And then we know that it is then heated isovolumetrically back to its initial pressure. Okay, so it's an isovolumetric heating. Sorry. Isovolumetric heating. Then enter state C. So for state C, pressure, volume, and also temperature. We know that the pressure is back to its initial pressure. So initial pressure was 38 times 10 to the power of 3 Pascal. Then we know that because it's isovolumetric means by the volume is kept constant. So the volume at state C will be equals to the volume at state B, which is equals to 22.5 times 10 to the power of negative 2 meter cube. Then the temperature is what we are not sure, so we leave temperature as blank. Okay, so this way we are able to show everything clearly in a table. So we say how many states? We have 3 states and 2 process. So initially is in state A, you have this pressure, this volume, this temperature, undergo isothermal expansion, enter state B. So state B has its own pressure, volume, and temperature. Then after that, undergo another process, isovolumetric heating, enter state C. Then state C has its own pressure, volume, and temperature. Okay, so once we know that, there's something else that we can study as well, which is what kind of process, what kind of equation can be used. We know that in between A to B, from A to B over here, because it's isothermal, you know that temperature is constant. So because temperature is constant, what you can know is that temperature is constant. You can follow Boyle's law, which says that pressure volume is equals to pressure volume. So in this case, PAVA is equals to PBVB. Okay, at the same time, you know that from B to C, from state B to state C, volume is constant. So if volume is constant, we know that it should be pressure divided by temperature is equals to pressure divided by temperature. So this is PB, TB, PC, Tc. Okay, so we know what is constant, then that value that is constant will not be in the equation. So let's say temperature is constant, so temperature will not exist in this equation. If volume is constant, volume will not exist in this equation. Okay, so this is a table that summarizes everything that is mentioned inside this statement over here. So first question asks you to state a labeled PV graph of the thermodynamic process. So they ask you to sketch a labeled PV graph. So means by you need to show the pressure volume at state A, pressure volume at state B, and pressure volume at state C. The problem is we still don't have pressure B, right? So it's best that we find pressure B right now by using this Boyle's law equation over here. So for question A, what am I going to do? I'm going to do PAVA equals to PBVB. So pressure A is equals to 38 times 10 to the power of 3. Volume is 7.2 times 10 to the power negative 2. Pressure B unknown. Volume B is 22.5 times 10 to the power of negative 2. Okay, so we can determine pressure B from here. And I believe if you put it into your calculator, you find that pressure B is equals to 12.16 times 10 to the power of 3 Pascal. So once you have obtained the pressure, volume, and pressure volume, what you can do is to sketch the PV graph that was required by the question just now. So you have your graph of P against V. P represents pressure. So we are going to keep it consistent by saying that it's times 10 to the power 3 Pascal. Then for volume, we are going to keep it as times 10 to the power of negative 2 meter cube. Okay, so once we have specified that, the next step that we should be doing is to label all points A, B, C on the graph. So we know that the initial pressure is 38. 38 is the largest value among all the pressure that we see here. So we can label it as 38 over here. Then after the volume is 7.2. 7.2 is a smaller value among all the other volumes that we see here. The volume here is 7.2, here 22.5, 22.5. So 7.2 is the smallest value. So 7.2 is over here. So if you connect the dots, you see that point A is over here. Okay, so let's continue. You enter state B. State B here is 12.16 pressure. 12.16 is somewhere around here, a smaller value. 12.16. Then after that, your volume will be 22.5. 22.5 is a larger value. 22.5 is somewhere around here. So we can connect your dots once again. Then you'll find that here it's state B. Okay, then after that, for state C, you see that is 38 times 10 to the power 3 Pascal. So that's the pressure. Then the volume is 22.5, which is the same as this one. So I'm going to bring this dotted line above. So this is state C. Okay, so once you have determined where is state A, state B, and state C, you're going to connect the dots using lines over here. You know that from A to B is isothermal, so anything between A to B must be on an isotherm. Okay, an isotherm looks something like this. This is an isotherm. Okay, this is an isotherm. So for isothermal process, you must be on the isotherm in order to keep your temperature constant. So you can see that the arrow looks something like this. Okay, it's a curved line, it's not a straight line, it's slightly curved like this. Okay, then afterward from B to C is an isovolumetric heating. Isovolumetric means by the volume will not change, that's why it's a vertical line so that the volume doesn't change. So from B to C is going upwards. Okay, so make sure you draw clearly the line and also indicate the arrow whether it's going from A to B or B to A, whether it's going from B to C or C to B. So in this case, it's A to B, then B to C. This is our PV graph for the thermodynamic process. Okay, next, they ask you to calculate initial temperature of the gas. Initial temperature is TA over here. I'll probably do it around here. If I have a bit of space over here. So to find TA over here, you have pressure, you have volume, and I believe you have the number of moles. So we have PV and N already. R is a constant, then you can find your temperature. So what you need to do is just to use your ideal gas equation over here. Okay, so for question B, you can do PV is equals to nRT. Okay, so pressure 38 times 10 to the power of 3, volume 7.2 times 10 to the power of negative 2 equals to N, which is 1.2, R 8.31. Then you have your temperature, which is unknown, which is what you want to determine. So from here, if you key into your calculator, you get the temperature at state A to be equals to 274.37 Kelvin. Okay, so that is question B. Okay, next you can move on to find the work done during the isothermal process. Isothermal process is from A to B. So what actually you want to find here is actually you're finding the area under the graph from A to B. This is what you're trying to find. Okay, of course you can go through the integration process to determine it, but actually you have already derived the equation in class, so you can just apply the equation that you have learned, which is for question C, you're asking for work done from A to B. This can be equals to nRT. nRT from A to B, so the temperature of A is same as temperature of B, no worries, ln. Then because it's from A to B, you're going to take V final divided by V initial. V final is B, V initial is A. So this will be the equation to use. So you know that it's 1.2 mole, 8.31 for gas constant. The temperature is what you determine in question B, which is 274.37. Ln, you have the volume final. Your volume final for process B, for process AB, the final volume is 22.5 times 10 to the power of negative 2. Then your initial volume for process AB, which is state A. For state A, your volume VA will be 7.2 times 10 to the power negative 2. Okay, so you have everything key into your substituted into your equation. It's just calculation. You get your work done to be equals to 3117 joule. Okay, you can see here this work done here is a positive value. So because it's a positive value, it indicates that it's work done by the system. The system itself is doing work. How does a gas system do work? It's by hitting onto the container, making the container wall move away from it. So it causes the container to expand, the gas container to expand, or the volume of the gas container to expand. So as you can see here, you go from 7.2 times 10 to the power negative 2 meter cube to 22.5 times 10 to the power negative 2 meter cube. It's an expansion. Expansion means by the gas is pushing the wall apart. So pushing the wall means by the work is done by the gas system. That's why it's a positive value. Okay. So for question D, calculate the heat involved during the isothermal process. So heat involved is Q. We know that to talk about Q, we need to come back to our first law of thermodynamics, which is delta U is equal to Q minus W. Because it's isothermal process, we know that isothermal, there's no change in temperature. Okay, isothermal, no change in temperature, so delta T is equal to 0. So because delta T is equal to 0, if you use the equation, delta U is equal to F over 2 nR delta T, you see that if this is 0, this will be 0 as well. So delta U will be equals to 0. So delta U is equals to 0. 0 is equals to Q minus W. So Q will be equals to W. Okay, so you have determined W to be 3117 for process AB. So the heat released during the isothermal process will be just equals to 3117 joule. It's the same value as what we determined for C, because through this derivation, we already determined that the heat that flows into the system will be equals to the work done by the system. So we know that the work done by the system is 3117 joule. So we know that the amount of heat that flows into the system will be the same value, which is 3117 joule. Okay. Question E. What process can be done to return the gas to its initial state? So what we have here is this graph over here. What the question is asking for is, if I want to go from C back to A, what kind of process can be done? Well, to go from C to A, what you need is a horizontal line that connects C and A, right? So for this horizontal line, we see that what is being kept constant? On this line, you see that every single point on this line refers to the pressure of 38 times 10 to the power of 3 Pascal. So that means by the pressure is kept constant. So if pressure is being kept constant, we know that this is a what kind of process? This is an isobaric process. Isobaric, your pressure is constant, but this is an expansion or a compression. Well, you see that the volume decreases from 22.5 times 10 to the power negative 2 meter cube to 7.2 times 10 to the power negative 2 meter cube. So the volume decreases. Volume decreases is definitely a compression. So this is an isobaric compression. Okay, so this is how we systematically solve this question over here. As I mentioned, it's always important for you to construct this table to show the pressure, volume, and temperature for each state and what kind of process is undergone to go from one state to another state. So once you have listed down clearly, you can determine what is constant and determine what law is suitable to be used. Once you've determined all this, the rest is just mostly just gas law, ideal gas law, plotting graph, or finding work done based on the equation that you have learned from the concept video. Okay, so that's it for now. Thank you very much.